This lecture describes experimental evidence for the existence of both time dilation and length contraction. It is based on detection of subatomic particles called cosmic ray muons. In previous lectures, we derived expressions for time dilation and length contraction. When objects are in relative motion compared to us, time appears to tick more slowly for them compared to us, and lengths are contracted along the direction of motion. Each of these effects is controlled by the gamma or Lorentz factor. So this example follows very closely the notes of Michael Fowler on page 27 of his special relativity lecture notes. So he writes, "The first clear example of time dilation was provided over 50 years ago by an experiment detecting muons. Muons are particles produced at the outer edge of our atmosphere by incoming cosmic rays hitting the first traces of air. So cosmic rays are high-energy particles that stream in from other parts of our galaxy at very close to the speed of light. When they collide with the nuclei of air molecules, a shower of different unstable subatomic particles is created, and one of those unstable particles is the muon. Muons have a half-life of 1.5 microseconds, which means that at a given time, if at a given time you have 100 of them, 1.5 microseconds later you will have about 50. 1.5 microseconds after that, 25, and so on. Muons are constantly being produced many miles up, and there is a constant rain of them towards the surface of the Earth, moving at speeds very close to that of light. In 1941, a detector placed near the top of Mount Washington at 6,000 feet elevation measured around 570 muons per hour coming in. These muons are raining down from above, but dying as they fall. So if we move the detector to a lower altitude, we expect it to detect fewer muons because a fraction of those that came down past the 6,000 foot level will die before they get to a lower altitude detector. So we'll draw a schematic diagram showing Mount Washington at 6,000 feet elevation and then sea level down below. The idea is that muons are constantly raining down from high up in the atmosphere, and some of them will decay right below the 6,000 foot level, but then others will make it farther down. Some of them will make it all the way down past sea level. So again, the experiment on top of Mount Washington measured 570 muons per hour. When they repeated the experiment at MIT, which is close to sea level, they measured around 400 muons per hour. We would like to use the measured data that's given here to see if these two rates, 570 muons per hour and 400 muons per hour at sea level, are consistent with this muon velocity and the half-life according to classical physics. Before we begin the calculation, it'll be more convenient to convert the speed of light from meters per second to feet per microsecond. We'll use the conversion that 3.28 feet is 1 meter and 1 microsecond is 10 to the negative 6 seconds. We find that the speed of light is approximately 983 feet per microsecond, or about 1,000 feet per microsecond. We want to calculate the flux of muons at sea level. We'll use the fact that every half-life corresponds to a reduction of flux by 1/2. Thus, after 1.5 microseconds, which is the half-life of the muons will have traveled approximately 1,500 feet. After this distance, the flux of muons will have been reduced by approximately 1/2. We'll define F naught as the initial flux of muons at 6,000 feet. If we wait 2 half-lives, the muons will have traveled 3,000 feet, and the flux will be reduced by another factor of 2, or 1/4 of the original value. Waiting 3 half-lives, the muons will have fallen 4,500 feet, giving a flux of 1/8 of the original value. And after 4 half-lives, the muons will have fallen 6,000 feet, meaning they will have reached sea level and the flux will be 1/16 of the initial value. So at sea level, classical physics predicts that the flux of muons should be 1/16 of the original 570 muons per hour, or in other words, 36 muons per hour. The group at MIT measured 400 muons per hour, but classical theory predicts that only 36 muons per hour should survive at sea level. So in other words, the observation showed more than 10 times the flux of muons than what classical physics would predict. Let's see if special relativity can do any better. We know that the speed of the muons is approximately 99.4% the speed of light. This gives a gamma factor of about 9.1. Let's consider the experiment from both the Earth frame of rest and the muon frame of rest. In the Earth frame of rest, the muon is traveling downward at a speed of 99.4% the speed of light, and it travels a distance of 6,000 feet from the top of Mount Washington down to sea level. In the muon's frame of rest, the Earth is traveling upward towards it at a speed of 99.4% the speed of light, and the distance traveled will be length contracted to only about 660 feet. So we see that in the muon rest frame, it only has to travel 660 feet to go from the top of Mount Washington down to sea level. We can estimate the flux of muons that survive after traveling 660 feet from the law of radioactive decay. We need to estimate the time it takes the muons to travel the 660 feet. We can do this by setting up a simple proportion. So the ratio of the travel time to the half-life is proportional to the distance traveled divided by the distance traveled for the half-life. So we plug in 660 feet for the distance traveled, and we know from before that muons will travel 1,500 feet after one half-life. Thus T over the half-life is 0.44. We can now plug this into the equation for radioactive decay. The initial flux is 570 muons per hour, and we find that the flux at sea level in the muon rest frame should be about 420 muons per hour, which is very close to what was measured at MIT. This was the first direct experimental confirmation of Einstein's prediction of time dilation and length contraction. So it will be instructive to summarize what this scenario looks like from the Earth frame and the muon frame again, and compare as many quantities as we can. So in the Earth's frame of reference, the height of Mount Washington is 6,000 feet, and this is the proper length. It's the proper length because Mount Washington is at rest relative to the Earth. On the other hand, in the muons frame, Mount Washington and the Earth are rushing towards it at 99% the speed of light. Thus, the height of Mount Washington will be length contracted down to only 660 feet tall. The half-life of the muon is assumed to be measured in the rest frame of the muon. The apparent half-life in the Earth's frame of reference will be the time-dilated version of this. We call it T1/2 prime. So it'll be 1.5 microseconds times 9.1, which is the gamma factor. And this approximately equals 13.7 microseconds. So we see that in the Earth's frame of reference, it takes longer for the muon to decay in our frame because of time dilation. This is why the muons can survive the trip from the top of Mount Washington down to sea level. In our frame of reference, the muons have a much longer half-life, 13.7 microseconds. Thus, far fewer will decay in the time it takes them to travel the 6,000 feet. How long does it take the muon to travel from the top of Mount Washington down to sea level in our frame? The time equals the height of the mountain, 6,000 feet, divided by the velocity of the muon, 1,000 feet per microsecond, or about 6 microseconds. In the muon's frame, we can do a similar calculation substituting the height of Mount Washington in the muon's frame, which is only 660 feet, divided by 1,000 feet, gives 0.67 microseconds. Notice that the time-dilated time equals the proper length over v, while the proper time equals the length contracted length over v. Alright, up next is the twin paradox.